whatever. And I just reminded myself to do the recording. So those are the norms for today. All right. So as a quick introduction, my name is Daniela Duran. I work with the Nano at Stanford site, which is a network of open access facilities and expertise, which means we have really fun and amazing research grade tools that can do some really amazing things that allow researchers, academics, industrial startups, and so on to push technology forward. And there is a potential summer program for middle school teachers that if you're interested, you could apply for at our site. We have both a virtual and an in-person. If you're interested in seeing what our community college students are doing, this might be of interest to your students. We have an Instagram that our community college interns have started that kind of appears a day in the life of what it's like to work in these facilities. So please feel free to take a look at that. Next slide, please. And just as a super quick introduction, I'm the Director of Education Outreach. I was most importantly a high school teacher for 25 years until just a year and change ago. So I truly appreciate the work, the enthusiasm, and the excitement that you bring to your students every day to get them interested in science and technology. And if you need anything, please feel free to reach out to me. We'll be providing emails and such at the end on the resource document. So I will go ahead and hand that over now to Dr. Zach Gray.
Awesome. Thanks, Daniela. And so thanks everybody for joining in today. As Daniela stated, what we're going to do is we're going to talk a little bit about nanotechnology, how small nanometers really are, and then why we need these kind of high-powered machines to see at this scale. And one way you can do that, and the most economical way, is using this thing called the RAIN network. And we're going to get into that today. So I'm going to talk to you guys for a few minutes about nanotech, small scales, and then I'm going to turn it over to Lauren, who's actually going to use an electron microscope in real time and show you guys how we do this. So just to introduce myself real quick, my name is Zach Gray. I'm the managing director for Penn State's nanofabrication program. We've been running this program since 1998, teaching 2- and 4-year students all things semiconductor processing and nanotechnology. We've had over 1,000 students take this class. I actually was one of them. I took this course about 15 years ago. And ever since I got involved in nanotechnology, I've been doing nothing but nanotechnology. So it's a really, really great field. And what we want to do, one of the motivations for this whole talk today is we'd like to get students at the high school level knowledge about all this, because many times high school students aren't even aware of what nanotechnology is. So first thing I'm going to talk about is the nanoscale itself. So nanotechnology is formally defined as the branch of technology dealing with things less than 100 nanometers in size. And this often means individually manipulating atoms and molecules, so just incredibly small. The formal window for nanotech is 1 to 100 nanometers. So basically, if something is in that range, it's defined as nanotechnology, as long as it has one dimension in that range. Now, I will state as a disclaimer, in the nanotech world, very often we work at a size scale larger than 100 nanometers. And like today, for example, we're going to look at an SEM, and the majority of what we're going to be doing is actually larger than 100 nanometers. But the reason 1 to 100 nanometers is important is because that's where the really weird stuff happens. And we're going to talk about what those things are. But before we do that, we need to understand the concept of scale. Obviously we all know a nanometer is like really small, but how small is a nanometer? So a couple ways to look at it. A nanometer is to a meter as a marble is to earth. I think the next one's really interesting. So a nanometer is how much your fingernail grows every second. So just kind of think about how small that is. I've been talking to you guys for what, like 3 minutes so far? So in the time I've been speaking to you, all of your fingernails have grown 180 nanometers or so. Yet nanotechnology is building things that's 1 to 100 nanometers, smaller than how much your fingernails grown since I've been speaking to you. It's almost unfathomable how small this size scale is. But the reason it matters from a technical standpoint is because when things get this small, the surface area to volume becomes very large. And what that means is more of the chemical bonds are at the surface of the material, and that does things like make the material more chemically reactive. And the other thing from a technical standpoint is once things get below 100 nanometers, the quantum effects start to come into play. And basically, quantum physics it just means weird. Things start to behave abnormally. So here's the periodic table. We've all probably had to memorize some of these over the years. I know I certainly did. But what happens is when you take any of these elements and you make them 1 to 100 nanometers in size, all of their properties are different than what we're used to. So we call these elemental properties. So these are going to be things like the melting point, the fluorescence, the electrical conductivity, so on and so forth. Every single one of those things, when the element is made 1 to 100 nanometers, is different than it is at the macroscopic scale. So the way I like to think about this is it's almost like nanotechnology is adding a new dimension to the periodic table, where we have the periodic table as we know it, and then we have this whole tapped world of new stuff we can do when we make these elements small. And for the sake of time, I'm just going to real quick go through one example of one of these. So let's talk about gold. We all know what gold looks like. It's in jewelry and it has this really nice color. It's expensive, it's valuable. But this is gold at the bulk scale. So this is gold, in everyday life. But what happens is if we make gold 1 to 100 nanometers, i.e. nanoscale, it's totally different, and that includes its color. So what this little diagram is showing is that as the size of gold changes, its color actually changes, which is really neat. And this is kind of quirky and weird, but who cares? What's the point of this? Well, they actually use these color changes in biomedicine. They're using this in disease detection. Cystic fibrosis is a very, very common disease, and they're actually testing for cystic fibrosis using the complementary DNA and these color changes of gold nanoparticles. These are used in stained glass windows. They're used in the pregnancy test kits. So gold nanoparticles are used all over the place, more in everyday life than you may realize. But there's an issue with all this. The nanoscale is 1 to 100 nanometers. But the human eye gives up. So you guys, you think about the meter stick, and the smallest tick mark on the meter stick is the millimeter. The human eye cannot see something smaller than about 3% of 1 millimeter. So if you do the math on this, 3% of a millimeter represents the tiniest speck of dust you can possibly see. And if we convert 3% of a millimeter to nanometers, you're going to get an answer of 30,000 nanometers. So there's no way you can just squint and do this nanotechnology stuff. It is not possible. You need high-powered machines and microscopes to see at this scale. And that's what the RAIN network is for, is to enable students to see at these scales beyond the ability of the human eye, beyond the ability of a magnifying glass, and even beyond the ability of a conventional light microscope that you may have in your bio labs or chemistry labs. So 30,000 nanometers, every day we measure things with a tape measure. This is characterization at the scale of everyday life. You cannot use a tape measure to measure nanoparticles. The resolution is far too poor. Instead, in nanotechnology, we use electrons, a beam of electrons as our source. This is a picture here of an electron microscope. So you can see the resolution is a lot better, but there's obviously a caveat. Which one do you think costs more? Well, it's obviously the electron microscope. Typically, these things cost on the order of over $500,000, whereas a tape measure is, very affordable. So because these things are so expensive, it's not practical for them to be sitting in a high school or sitting even in community colleges. Most universities don't even have one of these things because they are extremely expensive. And that's the value of the RAIN network, is these things are available to use for student education free of charge. Basically through a resource sharing model where you can send samples to one of these universities, to someone like Lauren, and she can pop your sample into one of these high-powered machines and get these images to do nanotechnology education. So just to show you why these microscopes are so powerful, these are two images that I collected. The image on the left is an image I obtained with a regular light microscope. And this is at 100x magnification, which is the highest magnification, highest magnification of these microscopes. And then the image on the right is the same exact area. This is a steel mesh with a little particle in it. look how much better the image on the right is obtained with one of these electron microscopes. The only way you're going to get an accurate diameter measurement of that particle is by using something like an electron microscope. So we need these for the enhanced resolution to do the research in this cutting edge technology. So one more, and then I'm going to quickly talk about how to use the RAIN network, and then I'm going to turn it over to Lauren. This is one I enjoy doing. I do a lot of outreach across the state of Pennsylvania, and I work with students trying to get them excited about this field. And I like to show them this one. So I show them this picture here, and I say, what is it? And everyone gives me a blank stare, and they're like, I don't know what this is. It doesn't look like anything. Because it really doesn't, right? It's just like this gray screen of nothingness. But what happens is at the nanoscale, there's a whole different world. Things look totally different than at the scale of everyday life. And you can see there's a couple little particles, but it doesn't look very interesting. So I start to zoom out a little bit and show a little more of the object and hope someone can guess what this thing is. And still, usually most people don't know. Some people might say, oh, it kind of looks like a nose. And then I zoom out a little more and it starts to take form. And you can see what this actually is this is actually a coin as image. This is a stitched image obtained from an electron microscope. And this is what a dime basically looks like when imaged with one of these machines. And for the sake of everyday life, we don't need this high resolution. But at the nanoscale, every single one of these little black spots, and for the record, this is the exact same dime, every single one of these black spots represents something humongous compared to the scale of nanotechnology. Therefore, we need to know what's there. And that's why we use these high-powered machines to see at the nanoscale. So these trivial features are huge at the nanoscale. How do you get these types of images? How do you show your students this type of resolution? That's where the RAIN network comes into play. So the RAIN network stands for Remotely Accessible Instruments for Nanotech, and it's free of use to everyone. It's this resource that's been around for a long time, but quite frankly, not enough people know about it. What's cool is you don't need any complicated software. There's no plugins. All you need is an internet connection and a desire to learn, and you can take advantage of this network. And not only can you see these images, your students can literally control the machines. They can be the ones zooming in on the sample. They can be the ones taking the pictures. And that's really where a lot of the learning happens, is when your hands are the ones controlling the machine. This is a list of all of the every little black dot in this image represents a network node. So anywhere you see one. So right now, obviously, Lauren is sitting in I believe, San Diego, and she's going to be the one helping us out here in a few minutes. But these are all over the place. So if if your high school is located, for example, somewhere here in Texas, you can have your students rip out one of their hairs or something, or find an ant on the street, put it in an envelope, send it to Texas, and then they put your ant in the microscope and you look at it. That's the big idea of all this stuff. These are all the tools on the network. It's not just SEMs. I've been talking a lot about the scanning electron microscopes, and I will say they are by far the most popular tools on the RAIN network, but there's a lot of other stuff on RAIN. We have AFMs, atomic force microscopes, stylus profilometers. So EDS, which is basically an extra detector on the SEM, this is something that's really, really cool, because you can zap a sample with the EDS and it'll say, hey, your sample's 78% carbon and 22% oxygen, or whatever it might be. So EDS is a really nice tool as well that's typically found in conjunction with the SEM. So if you want to use RAIN, it's very easy to do. This website right here, you would visit this Nano for Me website. And then there's a button you would click, schedule remote session. And then it's a real simple form, basically where you're from, what kind of sample you want to look at, and what type of tool you want to look at it with. And you click go. And then what would happen is we would get that inquiry here at CNEU, and then we would get right back in touch with you and set up a RAIN session. It's as easy as that. Doesn't cost any money. It just costs a little bit of time in filling out that quick form. But now what I want to do is I want to pass it over to Lauren, and she's going to show you what one of these machines looks like in action. So I'm going to stop sharing my screen now.
All right. Okay, can you guys see that?
Yes.
Good. Okay, perfect. Thank you, Zach and Daniela, for this opportunity to share the remote SEM capabilities. I have been working on remote SEM for UCSD and SDNI, and UCSD is one of the top performers of the RAIN network. And then to just introduce myself really quick, I graduated this past June studying, and I studied nanoengineering and chemistry at UCSD. And now I'm working at the Salk Institute, which happens to be across the street from my undergrad institution. And then, yeah, sometimes I do outreach like right now. Okay. So Zachary kind of gave us a little overview of why the SEM is better as opposed to the optical microscope. But yeah, just to refresh real quickly, the optical microscopes, which are the ones that are commonly seen in classrooms, see at best 1000x resolution. And at best, the cone-shaped cells in human eyes can only detect wavelengths from 380 to 700 nanometers. This gives us a light resolution of around a micron or a couple microns. And now why SEM has such higher resolution is because we use electrons instead of light. Electrons are much, much smaller, and more technically, they have a shorter wavelength than light does, or visible light does. The resolution of SEM is technically limited by the wavelength of an electron, but for practical reasons, and because of user issues, it's more limited by the electron sample interaction, since SEM samples have to be able to conduct electrical charges to some extent. We are able to look at samples, as you'll see in the live session. You're able to see samples that are not conductive naturally, but we can sputter coat the samples with metal so that you could see it in the SEM. So how does the SEM work? Basically, we're boiling electrons off a coil and shooting them down at the sample. And we have detectors that count the number of electrons that are received. And these electrons that are received by the detectors are scattered by the sample, or whatever sample of interest you have. And then you might have seen some pictures of the SEM and we're kind of wondering, why is it grayscale? Like, I want to see some color, But unfortunately, SEM creates an image by counting the number of electrons that are seen in one place versus another place. And because of that, we do not have a detector that translates those counts directly to color. A camera sensor, on the other hand, can sense different colors of light by the energy received. But for SEM, we are spitting electrons at the same energy and then simply counting the electrons that the detectors detect. Therefore, the images can only be black and white. White means more electrons and dark means less. So I guess if you have seen pictures of SEM images that are colored, they were probably photoshopped after taking. But yeah, let's get started. So I'll show you our SEM that we have over here. I apologize for the wobbly camera. I'm trying to hold it. But yeah, this is our machine. And then these are typical sample holders. We call them round carousels because they look like a carousel. But yeah, so each sample, except that B that's like stuck in the middle, is mounted to a small chip, which you can take on and off to customize which samples you want to look at. So yeah, let's get started. Okay, so on the screen that I have up here, this is the graphical user interface, or the GUI of the SEM microscope. So this is how we control the microscope with this screen and some other buttons that are on my side over here. And yeah, and that's how you can see it. So yeah, let's get started. All right, just to check, Zach, is the refresh rate okay?
Yeah, this looks great.
Awesome. Okay. And then also, please let me know if you have any questions along the way. You can either interrupt or type it in the chat. And yeah, if Zach and Daniela can watch the chat to stop me if I don't see it. All right, so Zach asked this question maybe like 5 minutes ago, but does anyone think they know what this is? Feel free to type some answers in the chat. I'm interested to see what you guys think. We got a scratch, an insect. Anybody else? A coin? A peanut? I can kind of see that. An ant? All right. Well, unfortunately, it's none of those things. It's actually a gecko's foot. And if you guys, I actually was in Hawaii this past summer, so I got the rare opportunity to see a gecko in real life. I don't know if, yeah, hopefully you guys can see this image, but yeah, I saw it sticking on the wall while I was eating my shave ice. So one thing that we've always been wondering, why can geckos stick to walls and climb upside down, but we can't? Like, that's kind of unfair. I wish I could be hanging from the ceiling right now. That would be pretty cool, like Spider-Man. But it turns out gecko feet and the mechanism that they stick to walls has been a nanoengineering controversy for years. So there was a lot of, like, between different scientists from different institutions, there was some fighting about what makes these geckos stick. Is it water-based forces like capillary adhesion, or is it intermolecular forces like van der Waals forces? So yeah, before I give you the answer to that, we will check out this image over here. So I'm first gonna focus it before we zoom in. All right, just to gauge the audience, did anyone think that this is how a gecko foot would look like? If you did, you're a genius. Because I certainly didn't. And before I actually started on the SEM, a lot of my classes talked about this nanoengineering controversy about scientists fighting over how the gecko sticks to walls. But I learned the reason, but now that I'm seeing it, it's just so much better. So we'll zoom in a little bit more. Okay. And also, by the way, the white spots that are on the right side of the screen, that is because a lot that occurs sometimes with these types of organic samples that we need to coat with metal. Oh, Zach, do you have a question?
Yeah, Lauren, a question came up. So how much of the gecko's foot is that we're looking at? What percentage of it?
Oh, like I'm not entirely sure, but I did take a look at the foot on the chip before I put it into the microscope, and it was like a dot.
Okay.
Yeah.
And needless to say, he's not with us anymore, right? No.
I don't know. I mean, the guy, I'm sure that the gecko could survive after
Just
losing this singular
One,
dot.
yeah.
But yeah, hopefully no animals were harmed in the sample making here. But yeah, so as you can see, there's some tiny structures going on here. Lots of stems with bundles of stuff. And those are called spatulae, because they kind of look like those baking spatulas that you cook with. And it turns out that geckos have hundreds of thousands of these. So the answer to the previous question is van der Waals forces, or intermolecular forces. And if you've taken any chemistry course before, you might remember this term and be like, wait a second, wasn't that one of the weakest forces that we learned about? Like we learned about the dipole and the hydrogen bonding, but van der Waals was always at the bottom. Like every chemistry teacher basically says that. So how are they able to use these forces to stick to ceilings and other surfaces? So as you can see, there are a lot of surfaces going on here, like in this small area that we're looking at right now. There's a high density of spatulae, as well as other smaller order nanostructures that we will zoom into later. And it turns out that because of these intermolecular forces that add up because of the large surface area that the gecko's foot covers, it turns out that the force from the van der Waals attraction is 1,000 times more than what's needed to hold up the gecko's weight from just gravity. So that's pretty cool. So let's zoom in on an individual spatulae.
And just while she's doing that, remember, she said the max magnification is 1000x of a standard microscope. If you look in the number in the bottom right, she's already about 4 times higher than the max you could ever get with a normal microscope. So she's already doing things you can't do with an ordinary microscope.
Okay, I'm gonna put it at a slower scan rate so that, yeah, the image comes out more sharp. But yeah, so now that we've zoomed in on, we're looking at small bundles of spatulae, or small spatulae. But notice that there seems to be another surface on the beams or the quote unquote beams that we saw. And it turns out geckos have a second order structure called setae, which are like, I guess it's kind of like going from tissues to cells, that kind of structural order. And geckos have hundreds of thousands of individual setae. But yeah, so that's kind of a nanoscale view of how these nanostructures cause van der Waals attraction between the gecko and the surfaces, and that's how it adds up to enable the gecko to stick on ceilings or other surfaces. So yeah, we can try to go a little closer.
Yeah, I was gonna say, proteins.
All right, so like, look at that high density of surfaces. And if you check out the bar down here in the bottom right area, where that sample bar is 200 microns. We can go even closer. And then as you can kind of see in that little bar, the smaller box that I'm focusing on, you can kind of see some movement going on, right? So that's due to charges moving of electrons and buildups of electrons. And that can occur for a couple of reasons. So the beam voltage is 4 kilovolts. So perhaps making it a little lower would get rid of that problem. But if you make the beam voltage lower, then you can't penetrate as much into samples. Okay. So yeah, I think that's as good as it's gonna get for this field of view, right? Oh man. Yeah, we have some smudging going on. Yeah. That can also occur because the sample, like if there's are tiny movements within the sample due to the vacuum or any other reason can cause that kind of thing. But yeah, the general shape is there, and we're looking at structures that are really, really tiny. So that's enough for the geckos. Yeah, there's the magnified view of the gecko foot. Let's move over to the next sample. All right, this one is kind of fun. So can people type in the chat what they think this is? Yeah, the people that said the shell of the sponge, that's pretty close. So these are radiolarians. So it comprises some zooplankton from the seas of La Jolla, which are right next to UCSD. And they're actually samples donated by the Scripps Institute of Oceanography, which is part of UCSD, but is the part of UCSD that's actually right next to the ocean and the dock. So they have lots of samples that they can get from there, and hopefully we can get more. But radiolarians are protozoa, or single-celled organisms that absorb silica from seawater to produce intricate mineral skeletons, which we will see as we go closer. We'll make sure to go around this sample so that we can see all of them. Let's zoom in. All right, let's look at this spiky one. Spiky sponge-like or sponge-looking one. At least I think it looks like a sponge. But for the radiolarians, some of them have spiky textures, and this is to increase the surface area for buoyancy so that they float, because these guys can't move on their own. They kind of just drift with the currents. And the spikes also help to capture prey.
So Lauren, quick question that came up here. Which of these things you're doing would a student be able to do remotely?
So actually all of these things, if we give there's only a couple controls, so these can all be done remotely. To like zooming in, moving, focusing on an image.
Okay, is it possible that a student could break this tool somehow?
Sorry, what did you say?
Would it be possible for a student to like press the wrong button and break this machine, or is it pretty safety interlocked?
You know, I don't think a student, like especially if we have someone on this end monitoring it, I think it should be fine.
Okay.
It's kind of hard to break the machine, which is good for all people. But yeah, here's our little shell, spiky shelled guy. Let's zoom out and go look at some other ones. As you can see, there's a diverse population. I guess this one looks more like a sponge than the other one. Okay, so this is a different type of, this is very different from the spiky shelled friend. And these things are really cool because they often have perfect geometric form and symmetry, like for this one, like the holes that are there. And it appears that it was broken off of some other piece, but yeah. Notice the symmetry of the other shells that we'll go to. How about this one over here? Yeah, well, it looks kind of funny. I see Daniela turning her head. See some other ones we can look at. Also, if anyone sees one of interest, let me know.
And just to clarify for teachers, I just put a question in the chat about how does the interface work? Is this all through the internet or do they have to download software, just from a logistical standpoint for a teacher?
Yeah, so for the teacher's point of view, it's actually pretty seamless. All you would need is an internet connection to a browser and Zoom. And then the software in our end will take care of it.
Lauren, when I did this with my class, they needed a mouse that scrolls. Is that true still?
You don't have to have a mouse that scrolls, because yeah, I'm not doing any scrolling or anything here, but yeah, I don't think you need one.
Even better.
Yeah, anyone? I guess we've probably looked at a decent amount by now. Maybe this one.
I mean, just communicate with them somehow. Like, there's gonna be a-
And then there was a question about, are you able to pass control over, like, for example, during this session, or does it have to be done beforehand?
Oh, like would I be able to pass the remote right now?
Yeah.
We'd have to, I think we'd have to set that up beforehand. Actually, I've not done like a live remote session where the users actually manipulate the buttons on the microscope. But yeah, we're trying to set some of those up. But yeah, this looks like a distant friend to that other piece that we looked at before. So yeah, that's the sea sediment.
Hello, everybody.
Oh,
Hello.
Hello.
I did the remote session last year with a colleague from Nano for me, I guess.
Oh, cool. Wait,
It was about atomic force microscopy. It's not like this.
oh, you guys used an AFM?
Yes.
And how did that work out for you? Was it through the internet, the way that Lauren had described, where you don't have to download
Yes, it
software?
was. He let me control the imaging and it was a graphical user interface. So I can see how to manage the control and how to zoom for some zones, etc. How to measure, etc. The feature cells or the feature size of how to focus on some zones of this image.
That's wonderful. And you actually bring up a good point. Lauren, is it possible to measure? Like, for example, if we wanted to measure, you know, that one of the spheres in front of us?
Yeah. So there is a tool, and on our microscope, it's broken for some reason. which is super sad, or else I would show you. But I can send some photos to you guys afterwards with some measurements that I've taken before the tool broke. But yeah, in theory, you should be able to do it from the remote session. So Daniela was kind of on the spot earlier when she said pollen, because now we're looking at some pollen grains over here. So briefly to discuss where pollen comes from and why it's important for plants. So there's the wind pollinated plants that get pollinated when their pollen gets blown by the wind, and then insect pollinated plants where an active insect goes in and takes it and then drops it off somewhere else. This pollen in particular is from a hibiscus, which is an insect pollinated plant. So if you guys have probably seen pictures of the coronavirus, and it kind of resembles the pollen grains a bit. But yeah, as you can see, the pollen grains here have all these little spikes on them. And it turns out that's actually it's a competitive advantage that pollen has. And that's because the spikes on the pollen grains help them cling to the bodies of insects or birds, and also help them stick whenever they're being deposited somewhere else. So it's actually really smart of plants to come up with this little tactic.
Yes, there was a comment that it looks like they're designed to make people sneeze.
That too. I mean, no wonder they do. They got all these pokey appendages sticking out. Yeah, here's one that's not like dented or broken in any way. We'll let the scanning finish out.
Now, if students found a really cool sample that they wanted to have that image, is that possible?
That's possible, yes. And we would encourage that because not many people in our network have actually taken advantage of it. So we would love to see what samples the students want to see, probably because we also would want to see them too. So yeah, that's it for the pollen. Oh, did somebody have a question?
There's one more question in the chat. I just have a screaming baby in the background.
Oh, okay.
The question is, I'm gonna let Daniela read the question. Apologies.
Okay, no problem, Maria. It says, are you able to cut into a sample to see inside? What is inside the pollen granule?
Ooh, that's a good question. We definitely can cut it, and we have not done that before. So that would be interesting. Like, yeah, I kind of wonder too, like, is it hollow or is it solid? Does anyone think they know what we're looking at right now?
And then there was a follow-up question asking, do you cut it in the SEM?
Oh, no. So the thing is, the SEM, in order to take these images, it uses a high power vacuum. So the chamber right now is vacuum sealed because we're using it. So we would have to do it separately. But yeah, I can't really see the chat, but if anyone guessed shark scales, then they're right.
Yes, there was dragon scales, reptile skin.
Oh yeah, you guys are spot on. Same like general concept. So yeah, if you ever talk to any people that work at an aquarium or marine biologists, they probably call shark scales dermal denticles because that's the scientific name for them. But as you can see, their shape resembles teeth rather than scales, which is kind of scary. But it turns out that there is an evolutionary advantage to having scales that look like teeth and are really sharp. And it's because this decreases the hydrodynamic drag as they're swimming through the water. Yeah, it decreases the drag and turbulence. So these two features allow the shark to swim faster and more quietly so that it can sneak up on the prey that it's chasing after. And then additionally, they serve as physical armor for the shark. So yeah, let's focus and go in.
And teachers, I'm sure we're all thinking structure and function as cross-cutting concepts, right? NGSS stuff in terms of all these different types of materials that we're looking at that are in nature and have these very specific structures that are tied deeply into their functions. So this is just an example of how you can connect some really cool technology with some concepts that you're probably teaching in your classes.
Yeah, that's absolutely right. And yeah, so now we've zoomed in on a couple of shark scales. And as you can see, there's some weird little blobs that are kind of sitting on the scales. And to be truthful, I don't actually know what those are, but I do have a couple of theories. Like it could be the metal, like the grains from the metal that we sputter onto it. Sometimes if they're not sputtered well or sputtered evenly, it can show up like this and we can actually see it. But yeah, the people that do the coding, they try really hard to make sure that it doesn't obscure the image that we're looking at. And in general, we can still see the shape and the texture of the shark scale, right? So let's go to one that's not.
So does having to sputter coat them degrade the samples at all? Is that one of the limitations of a high vacuum SEM?
Yes, it's definitely a limitation, but yeah, there's other. So like I think someone mentioned the AFM, the atomic force microscope, and in the lab that I work in, we work with DNA and DNA origami, so like 3D objects of DNA, and because they have to be in like in a water solution, we can't look at them with an SEM, or else we'd have to dry our sample out, and it might lose its structure. So the AFM is another good tool that I think they're trying to get that one to be remote access too.
There was a question about, do you have an image of graphene?
Oh, of graphene?
Mhm.
Yes, we do. I can include that in the photos that I send out to you guys. Those are pretty cool. But yeah, here's an individual shark scale.
Okay, so we've got about 4 minutes left with Lauren. So did anyone have any other questions as she's moving around to look at probably our last sample, I'm guessing?
Let's see, I'm gonna try to find a good spot on here. So this is a blue morpho butterfly wing. Oh, I think this is a better spot. And I'm sure a lot of us haven't actually seen a blue morpho butterfly in person, but we have a picture, I think it's an actual one that someone glued to a photo frame, but this is what they look like. So as you change like the perspective from which you're looking at it, the color is kind of glimmering, or it appears to glimmer in the light. So yeah, now we're gonna look into what nanostructures enable this color in the blue morpho butterfly. And it's not just random.
stays like this, and then
Ooh, we have a lot of charges.
yeah, I've tried. It's like,
Let me see if there's another area that's nice. It's better.
So it looks almost like the sample is tilted or angled. So are you able to tilt the stage and angle it?
You're able to tilt the stage, but for this one, since we are not trying to tilt the other samples, this one's actually mounted on a mount that goes like this, and then the butterfly wings pasted here. Okay, so in a way, it kind of also looks like shark scales when we zoom in closer to the butterfly's wing. And yeah, so as we heard earlier from Zach's presentation, visible light is in the nanometer scale range from about like 300 to 700 nanometers. And the blue morpho butterfly is an excellent representation of how fundamental structure, instead of a chemical like pigments or dyes, creates a color. So we're gonna keep going in on the wing. As you can see, there's all these little ridges that you can see on the individual, I don't know what you call them, feather, shark, scales, feathers. Okay, so as we get closer, we can see that there's these individual ridges in a highly ordered structure within this butterfly wing. So now, how does this structure here that we're looking at create the color that we saw in the actual butterfly? So it turns out that when light interacts with objects or specimens, some of the light diffracts and some of it interferes. It's all just a matter of light matter interactions. So in the case of the blue morpho butterfly, diffracted waves interfere with each other so that certain color wavelengths cancel out and aren't shown, while others are intensified. So the size and the shape of the gaps that are shown here, like in between the individual small ridges here, they directly correspond to what wavelength and what color that we see. Okay. But yeah, I took pictures of this butterfly wing earlier with a couple weeks ago when the measurement tool was working. So I will send those through, and they show like the horizontal distances between the two, like these two beams, and then the vertical distance between the inner spacings. So yeah, I know we're out of time, but if anyone wants to stay for like, well, we can try to make this quick because I think the camera pixel is really cool to look at. Do we have time, Danielle?
Yeah, go ahead and bring up that next image. And while you're doing that, I'll put in the chat a post survey and then a link to also a resource document. And the resource document is going to highlight some interesting events such as Nano Days. So Nano Days is in October. Well, Nano Day is technically October 9th because 10 to the negative 9. And so there's a hashtag National Nano Day that's trending, and there's just some different resources you can use to find out more about activities related to that. There's an image contest that's through something called the NNCI, which is a network that both SDNI and Nano at Stanford are a part of. That's really cool because your students get to vote on which images will win the national contest. And these images are taken with tools such as this one that you've just gotten to experience today. All sorts of different tools though, but there's some really cool images. So the voting doesn't open until October 6th, but there's a link and just some samples from last year for reference on the image document. So let me put that in the chat. And then Maria, did you want to add anything? Did I miss anything?
No, thank you. In addition, I think in the package that you sent out, there should be a link to the National Nanotechnology Day website in nano.gov. Thank you.
Great. Okay, yes, in the source there is a link to that under other resources. And there's also a link to other, looks like, oh, the slides, of course, that Zach went over earlier. And then also a link to the post survey in case for some reason you can't get the chat to pull it up. But we do really appreciate your time today because we know you have many, many, many things to do as an educator. And I just want to reemphasize that this can be a tool that can really bring wonder to any level of student, high school, middle school, even elementary school. I did outreaches with elementary students with scanning electron microscopes. So it's definitely something that can hit at all ages. So it's now 3:30, so I will hand it back over to Lauren for those that want to stay and take a look at this cool image. And I hope you had an enjoyable time and have a wonderful week. So
Yeah,
over to
thank you.
Lauren.
All
Thank you
right.
so much.
So for the people that wanted to stay, so the individual squares that you see here are individual camera pixels from like your phone camera. And they're made of silicon. So the silicon's one of the main semiconductors used in the industry of electronics. And yeah, I just think this is a really cool image and something that students would be interested in because we all have cameras these days, whether it be on a phone or a tablet. But yeah. And then the digital pictures that we see consist of millions of these pixels in different colors and different color intensities, which make up what we see on a screen. So yeah, thank you guys for attending and for listening to the presentation. And yeah, the key takeaway is we need to understand nanoscale interactions to use them as a tool for advancing society, whether that's in biomedicine, pharmaceuticals, material science, semiconductors. The list of applications is endless. So yeah, thank you. And hopefully your students will utilize this tool to understand structure, function, relationships in hands-on activities. Thank you, guys.
Thank you, Lauren. That was wonderful. I learned some really interesting facts that I didn't know. And I also forgot to mention that we will be posting this recording so that you can, I think I mentioned it in the chat, but I'm not sure. That way, if you wanted to highlight some of the really cool examples that Lauren just showed you, and then you could take it a step further and sign up with the RAIN network to actually have your students drive the tool. So thank you to everyone who helped organize this, Maria, Zach, Lauren, Marielle. I appreciate that, and I hope everyone has a great day. So take care.
Thanks. And thank you, Lauren. That was terrific.